Hello everyone, I believe I'm now live. My name is Nick Tucker. I am an Associate Professor in Materials and Manufacturing at the School of Engineering at the University of Lincoln, and it is my pleasure and delight to introduce you to the engineering perspective of material science and manufacturing. So I'm going to turn my camera over to our demonstration apparatus today. We'll just have a quick look at that. This is our Instron, well, one of our Instron tensile testers, and that tall column contains an Acme screw thread, the thread form we use for transmitting loads, that's driven by a motor in the base. So I can move these jaws apart, and this item here is a load cell that measures the load. Effectively, it's a weighing machine. If you're an electronics fan, it's a Wheatstone bridge, and we'll come back to that later. I will leave it pointing at the apparatus. So what it enables us to do is it enables us to relate force applied and distance for material testing. So I will now go to my set of slides, and the alliterative title is to indicate that we need to know about the structure and properties of our materials if we're to sensibly be engineers. So this is the structure of the talk. Need to have a little bit of a talk about engineering because it is different to science and technology. Introduce the talk. Have a little bit about polymers. Our test materials are polyethylene and polystyrene. We'll have a demo. We'll explain why they're different, and I'll give you some further sources of information if you want to take it a bit further. So the first thing is the purpose of engineering. What's it all for? If we think about this, science, that you've all no doubt got some experience of, is what we use to describe and make sense of the world. And part of the language we use to cope with that, to put some figures on it so we can predict, we can model, we can quantify, is mathematics. And if we apply the science to do something, that's technology. And engineering is using science and technology to make money. That's what it's about. We are at the commercial end of things. We are thoroughly conversant with technology, fairly well with science, but as engineers, what we're doing is we are performing activities that make a few bob. So if we're going to be effective engineers, we need to understand how material prices vary. You'll be familiar with petrol prices going up and down. It affects the transport cost. We need to have an eye towards the world economy to make sure that we're as prepared as we might be if there are going to be variations in raw material price, variations in the market that we're selling into, and political and economic variations. Suppose somebody suddenly puts a tariff barrier between you and your supplier. It's important you're aware that this is going to happen to take the best steps to cope with it. We also need to know why materials have particular material properties and how they're likely to vary. If you think about making things out of steel, we can start with a steel that is a nice, soft, machinable material. We can machine it to the shape we want. And then if we take that steel and we heat it and then cool it really, really quickly, we cause a preferential reduction in grain size, molecular level alteration that can mean that we can achieve essentially still a tough material, but the outer layer will be phenomenally hard. If we're looking at making a knife blade or something, it'll keep a good edge. If we're looking at making a bearing, it won't wear out too quickly. So that's the sort of stuff that we need to know. That takes in my third point as well. And I guess, just to hammer the point home, the structure at the atomic level varies according to material grade. We move away from the simple concept of elements. We move to alloys. We move to various proprietary recipes. And we need to understand that. The processing conditions I just alluded to. Service conditions are important. If you open your car bonnet, you'll see an awful lot of black plastic covers under there. They're all nylon, technically a polyamide, quite an expensive plastic actually, an engineering material. The reason is that the typical under bonnet service temperature for your car is reckoned to be 140 degrees C. We need to use an expensive, high performance polymer, essentially so it doesn't soften or at worst melt under normal service conditions. Environmental exposure is important, particularly with our polymers. Some of them are quite sensitive to UV light, ultraviolet light. They may well become brittle and friable under UV light. We'll look at solvent resistance in a minute or two. So we need to be conversant with all these things if we're going to be any good at our job. So in this talk, we're going to first of all look at costs, because they're very important to us. That's both in terms of raw materials and manufacturing. We're going to look at factors that affect availability of the materials. And once we're confident about that, we can think about the property variation, and we'll also have a little nod to environmental impact, because that is vitally important to us on account of there is no planet B. The little cube on the right is a diagram by a fellow from Cambridge called Mike Ashby. You should look him up. He's very good on material science. He's very good at comparing different properties. That's what those little graphs show. So we're talking about polymers. Polymers are principally made from oil. About 7% of the world's oil production is used to make polymers. About 4% of that is actually ending up as your plastic washing up bowl, and 3% of it is the energy cost associated with processing and transport. So we can see that from this diagram or map culled from the very useful CIA World Fact Book, that oil's fairly well spread over the surface of the planet. But when we look at our usage on the left, we can see that we are just, the black band is mostly oils. They're actually talking about it in terms of energy consumption, but it fairly well maps over materials as well. And the indication is that we are very much likely to start using less of it to avoid choking on our own effluvium. And that's likely to have a significant effect on the availability and price of oil as a raw material to make our plastics. And you look at that chart on the right of the top 5 crude oil producing countries. You can see the yellow line is Iraq. When there was a war there, it knocked their production for 6 and caused other countries to start ramping up their production. Yeah, it used to be quite simple. It used to be, you know, we're definitely heading for scarcity of oil, and the prices will definitely rise. You can see from that graph it's not quite as true as we once thought, but we still need to consider this, because it's going to have a knock-on to the cost of our raw materials. So here are some data on the dark line is ethylene, the raw material to make our polythene from, and the I don't know, what would you call it? Yellowy coloured line is the actual price of polythene, and you can see it varying. You can see it dropping towards the beginning of last year, and now starting to rise again. Very tempting to view that as an effect of the COVID virus and the depression in people wanting to buy stuff. The price we pay, well, as I just alluded, depends on world market conditions, depends on where you're buying it from. If you're buying from DSM in Holland or BASF in Germany, we've now got a tariff barrier between us and them, so prices are likely to go up. There are an awful lot of grades of material. Going and asking to buy some polyethylene is a bit like going to the pub and asking to buy some beer. The bar staff or the polymer merchant will need to know in a little bit more detail what you want before they're able to assist you in the manner desired. Also, quantity is important. As an academic, it is fantastically troublesome to get hold of small quantities of polymer. Nobody wants to sell you 5 kilos or 25 kilos, really, because the cost of paperwork is the same as if I bought a 30-tonner full. So consequently, if I was able to go and say, certainly I'd love some, I don't know, Hastel oil, whatever it is, and I'd like a 30-tonner a week for the next 20 years, I would get a much better price than I do trying to buy a sample for experimental work. So it all boils down to, in the industrial setting, how good your purchasing manager is. That the purchasing manager is a creature of great wonderment and beauty, who can do you some real big favours in sorting out prices if they're good at their jobs. So a typical polymer, I meant to draw your attention to it on that graph there, probably about 2 and 3 times the price of steel. But if you went to go outdoors to buy a camping mug, very likely you would see an awful lot of plastic ones and very few of the steel ones. Steel's the cheaper raw material. Why on earth are the plastic ones more popular? And the answer lies in the manufacturing route, that if I want to make that plastic mug, I make a mold, have an injection molding machine, and I just squirt molten hot plastic into the mold. 30 seconds later, the mold opens and a finished sellable mug in a choice of colours falls straight out. So the raw material is expensive, but the manufacturing is cheap. Compare it to our cheap material mug. I've got to buy sheet material in. I've got to cut it to form the cylinder that's the body of the mug. I've got to put a rim on it. I've got to cut a base. I've got to join the two together. I've got to cut a handle. I've got to form the handle. I've got to spot weld the handle on. And I might even need to put an anti-corrosion coating and enamel in the one we're seeing there. It might be, I think the steel was previously tin plated, but it is a long and complicated manufacturing process with many opportunities for things to go wrong. It completely overwrites the cost advantage. That's why when you go outdoors, you get a plastic mug and not a tin one. So polymers, a big old family of polymers, and we love these hierarchical diagrams. So polymers divided up into elastomers, thermosets, and thermoplastics. We're going to look at thermoplastics. The thermosets and the elastomers are a little bit different in that the transformation from solid to liquid, with a thermoplastic, it's just freezing. An assembly of molecules have an insufficient kinetic energy to be maintained in the liquid state, and they solidify. It's a reversible, repeatable process. For our thermosets and elastomers, what's happening is there's chemistry going on. So our typical example of a thermoset is araldite, the glue that you mend your boot soles with. And when you mix the resin and the curing agent, some chemistry happens, and the molecules are actually joined together by strong covalent bonds to form, in the case of a highly cross-linked material, or araldite. In the case of one that hasn't got very many cross-links, an elastomer, which notably exhibits a very large reversible strain. So it means if I stretch it, it snaps back again. These are rubbers. We're going to talk about thermoplastics, crystalline ones and amorphous ones. Both the ones we're talking about, polystyrene and polyethylene, are crystalline. Polythene's crystalline, polystyrene semi-crystalline. It means they, upon solidification, if we do it slowly enough, they form little areas of order crystallites. Haven't really got time to go into it. These you can look up on your own recognizance. Google it. So, if we're thinking about our beloved polymers, the structure of same, we take a monomer, the individual building block, couple of carbon atoms, carbon double bond between the carbon atoms, the remaining valence is filled up with hydrogen. With some well understood but by no means simple chemistry, we can oblige them to join together like a big string of beads to form a long chain molecule that might be up to 10,000 monomers in length. That's our polymer. Principally made of carbon, hydrogen, and oxygen, like the oil we've probably made it from. Just should mention it is possible to make polymers. Well, we're all polymers. Proteins are polymers. It is possible to make processable polymers from non-oil origin, non-fossil origin materials. It is done. A little bit more expensive than the fossil ones at the moment. As you saw from the diagrams I showed earlier, that's a situation that's likely to change. So our example ones, the top is polythene. I can wave, I think you might be able to see that on the camera. That's my tensile test specimen of polythene. We'll come to that later. Known, abbreviated as PE. Our recycling mark is number 2, and you can see a little sketch of the molecular structure that we looked at in the previous slide. All those AKA names, the allothon, the leucolen, the bore shape, are all trade names for varying grades of this material. Typical applications, plastic bags, squeezy bottles, things of that nature. Our polystyrene, also available as polystyrene foam. We might get a chance to address that in a second or two. A little bit more complicated structure. It's the same long backbone, the same long chain, but odd ones of those hydrogens are replaced by that ring group, and it makes the properties quite different. So, summary, on the left, our thermoplastics that are just tangled up long molecules. On the right are thermosets that the molecules are chemically linked into a network by strong covalent bonds. Let's park those for the minute. The molecular weight is not constant like it is for, I don't know, salt or something like that, because the chains vary in length. So we have a molecular weight distribution, and the longer the molecular weight, in a sense, the better our properties. That's what this table shows. It shows us that the physical state changes. The monomer is a gas at room temperature. By the time we've made it, it goes through a liquid, a grease, a waxy stage, and those long chains at the end. We've got a 3,500 unit long one at the end. It's definitely a plastic. You can see the molecular weight has gone up. My little graphs on the right show a change in tensile strength, the strength we need to pull it apart, that increases with chain length. And also, interestingly enough, the temperature at which it starts to liquefy goes up. So here's our polythene, that simple structure. What to say of it? It's a low-cost material. It's quite flexible. I've given you a link there. Whether you could quite catch that in the time available, another question. Here's the stress strain for it. So the stress is effectively the load. I'm pointing to my computer screen. What good is that? The left hand, the vertical axis, is showing stress, the specific load applied, and the one along the bottom is showing how much it stretches. And so we can see it resists stretching for a little while, and then suddenly it starts to stretch without much of an increase in load. And that's kind of interesting. We'll look at that in some more detail. Here, by way of comparison, is polystyrene. I'm wanting to get on to doing the demonstration. The point to take from this slide is look at that isotactic, all the groups on the same side. The structure is sort of similar but sort of different. You've got those side groups sticking out the side. Hang on to that side group thing. Stress strain curve quite different. It doesn't strain much, it doesn't stretch much, it takes the load until it breaks. Let's go back to well, I'm going back. So now what you can see is in my tensile test machine, I've got loaded a specimen of polystyrene, and I'm just going to start to put a load on it. You can perhaps see, can you see? You can maybe see the computer screen on the left, and the load goes on, and bang, it breaks. Highly satisfying, a big snap. In terms of our tensile test, not the ideal. Our tensile test ideally would break more in the middle. If I was doing this for measurable results, I would discard that result, but just for a demonstration, we're pretty good with that. I mentioned solvent resistance. Now's a good time to bring it up. Here's acetone, familiar to those of you who use nail polish. Our specimen is quite flexible and quite resistant to flexing. But if I take a very small quantity of acetone and put it on our sample, we now magically find that if I try that bending experiment, it snaps really easily. And you can perhaps see that there's been solvent damage on the surface. The acetone has begun to dissolve the polystyrene, allowing the formation of micro cracks, which means that our properties suddenly become rubbish. So you really wouldn't want to put polystyrene in the way of any form of contact with a solvent like that. Oh, here's our expanded polystyrene. So that's been made into a foam using hexane, and it's really good at absorbing shock, but with a bit of luck, I haven't tried this, it's actually very brittle. So if you're looking at a crash helmet doing its work, it's the absorbing that's the good bit, and the breakage means it has very poor fracture toughness. It's not done a lot to save your nut from damage. Let's start our polystyrene test, our polythene test, I beg your pardon. You should be able to see that. I'll go back to my presentation. So the two curves are quite different. And what I've done with that one, it's got that wasp stripe on it. I've drawn lines with a Sharpie 1 centimetre apart. And actually, rush. Do it slow, do it right. Let's just put a line on here so we can make sure that it's not slipping in the jaws. And at the moment, it is undergoing the same load application as our previous specimen did, and we'll leave that one go. The difference here is that because there are no big clumpy ring side groups in the polyethylene, the atoms, the long chain molecules can slide over each other. And I'm sure as good-mannered people, your parents inculcated into you the undesirability of playing with your food. But should you have a plate of spaghetti or a plate of noodles, you can try stirring it about, and you will observe that as you stretch out your spaghetti or your noodles between a couple of forks, it tends to organize itself into orientated strands. And that's exactly what we're doing here. We are giving our polythene sample the coiled up, low energy state, long chain molecules are having the chance to uncoil and stretch out. And that's what's happening during the drawing process that I'm showing on my little graph here. So we'll leave that one go. Not quite sure, can't see it very well. If you can see the graph, you can see it's the extension in millimeters is going up, but the load is stuck at about 400. So under that load, it just continues to stretch. So in summary, as engineers, we need to keep an eye on the outside world because awkward things are going to happen that will affect our supply of materials and the market we're selling into. In terms of our polymers, the molecular structure of the polymers has got an awfully important effect on the macro scale properties, and as designers and manufacturers, we jolly well need to know about this. That's funny. When I prepared this slide, that was an animated GIF that showed it from that showed things stretching. If you want to know more about polymer properties, there's a very, very good and free website called campusplastics.com that has got manufacturers' data on a colossal number of polymers, and it's available free to use for the benefit of the world. If you want to know a bit more background, if you want to know the industry viewpoint, I would recommend you look at Plastics Europe, the Association of Plastic Manufacturers, which is www.plasticseurope.org. If you want to know a bit more about the environmental perceptions, because obviously the plastics manufacturers are going to be plastics, they're right enough, don't worry, nothing to see here, please move along. I recommend you to the Ellen MacArthur Foundation, ellenmacarthurfoundation.org, and there is an absolute ton of interesting information and data for you. Not quite sure about what your background is. This is a non-technical historical introduction to plastics. Plastic, the Making of the Synthetic Century. It's a book by a bloke called Stephen Fenichel, published by Harper Business back in 1996. It's an olden days book, but it's very good on the early days of the history of plastics up until the mid-90s, which is quite recent. It's quite a mature technology. So thank you for that. If you have any questions whatsoever, I am delighted to answer them. And we have about another few minutes before this will actually snap, but the typical extension will be about 100 millimeters. We're only up to 60. I could have done the start and that test a little bit earlier. Any questions? If we persevere with this long enough for it to snap, one of the interesting things is we will see that some of the strain is reversible. So what will happen is when it snaps, the broken ends will shorten again. It takes time for the atoms of the molecules to settle down into their new configuration. So equally, if you try this experiment on a bit of plastic bag or the harness from a 6-pack, if they still do those, you'll find if you apply your load very, very rapidly, it'll just break. There's no time for the molecules to do any of this nonsense. If you do it nice and slowly, you will be able to stretch, let's say, a bin bag, a section from a bin bag into something that's 4 or 5 times its own length very, very easily. And you will also notice that once you've got into the state where all those molecular chains are in a long line, it's actually a lot stronger than it was. And you can buy a form of polythene, which is gel spun. The famous trade name is Dyneema, and it has some interesting properties in that it hardly stretches at all. It's a very, very strong material. If any of you are hang glider enthusiasts, you will probably find that the rigging lines on your hang glider are made for that. So we've got about another 20 millimeters to go before it will break. But you can see that, well, you can see it stretching. That my 10 millimeter lines are now nearly double that. So with the plastics, the early introduction of modern plastics, polyethylene was originally a very secret material. They only used, very difficult to make, a lot of high temperatures, a lot of high pressures. And the only use for it was as insulating elements for radar during the Second World War. That's about how old it was. So the prospect at that time of saying, oh, we'll make disposable shopping bags or anything from it was seen as frankly remote. Also, one of the difficulties is that plastics originally had a very bad reputation for being unstable. And so the polymer chemists went and beavered away on this and did an awful lot to improve stability. And now we're stuck with the microplastic problem where whilst things might disintegrate, they are not absorbed back into the carbon and nitrogen cycles, more particularly the carbon cycle. And well, the Ellen MacArthur Foundation will be highly informative about the persistence of micro and even nanoplastics in the environment. They're rather propagating through the whole thing. And we're now reaching about 100. Just beyond 100, it'll break. I'm not wanting to detract from the drama of it by talking over it, but as an academic, maundering on is a problem we experience, so I am carrying on talking. Back in the day when we had disposable plastic carrier bags from the supermarket, this was a good example to use with my students if they had heavy loads of shopping, that the handles of the plastic carrier bags used to exhibit this property. And also because they became a lot narrower, you know, all that extension has got to come from somewhere, and it comes from a declining width. They cut into your fingers most egregiously and made the journey home from Morrison's more disagreeable than it might be. Actually, this one is going very well. It's a very rare piece of plastic that will get beyond 110 millimeters. This one's doing fine. Looks like there's a bit of necking at the top, and there we go. And you can see that that bottom piece is relaxing back towards its original length. That relaxation will carry on over the next, I don't know, half an hour to 45 minutes, but it won't get that much shorter. Right, so there we are. I now really am done. The demonstration is good, and I thank you for your kind attention. And if, again, you have any questions, that would be great.